Hello everyone, I'm Norman Wahlberger and welcome to the Algebraic Calculus. In today's lecture we're going to apply what we know about finding tangents to curves to the special case of quadratic and cubic polynomial functions. And we're going to review some very fundamental and important facts about quadratics and then extend things to the somewhat more unfamiliar and more complicated situation of cubics. So let's motivate maxima and minima problems, which is what we're interested in today, with this very simple classical problem. What is the maximal area of a rectangular field of perimeter 40? So here's a rectangular field. Let's say it has sides x and y. Then the total perimeter will be 2x plus 2y, and if that's equal to 40, then x plus y equals 20. So the question is, given the constraint that x plus y equals 20, what's the maximal possible area of such a field? Now this is a somewhat elementary problem that actually doesn't require any calculus techniques to solve, and in fact it's really contained already in a remarkable identity that's pretty well 4,000 years old. That goes back to the Old Babylonian times. It's this identity here, that if you have two numbers x and y, then the product is 1/4 the difference between the sum squared and the difference squared. You can check directly that this is a true identity. And why does it help us? Well, because from this identity follows the following very general and useful principle, that if the sum of two numbers is fixed, then their product is maximum when they are equal. Why is that? Well, suppose that we know the sum of two numbers x plus y is fixed, so that this quantity here is fixed, and we're interested in maximizing the product. Well, according to this, if this is fixed, then the only thing that's variable on the right-hand side is the difference. And the difference squared appearing here means that this is going to be maximum when this quantity, this positive quantity that we're subtracting from here, is 0. We've got something and we're subtracting a positive quantity. That's going to be maximum when what we subtract is 0. That's going to happen when x equals y. So applying it to this case here, the sum is 20. The product is going to be maximum when the two quantities are equal. In other words, when they're both equal to 10, in which case we're going to get a maximal area of 100. And indeed, 10 times 10 is 100. That's bigger than 9 times 11 or 12 times 8 or any other combination adding up to 20. So even though this is a relatively simple example, it illustrates the fact that quadratic problems are perhaps amenable to direct algebraic manipulations. And that's a kind of a key point that we might want to keep in mind. So let's have a look at the general case of a parabola. A quadratic function of the form y equals ax squared plus bx plus c. That's the standard form. We'll often prefer to actually order things a little bit different, starting with the smallest degree. So sometimes we might write c plus bx plus ax squared. Geometrically, this is a parabola opening either down like this or up like this, depending on the sign of a. If a is positive, it opens upwards like this and it has a minimum somewhere. And if a is negative, then it opens downwards like this and it has a maximum somewhere. And we're interested in finding out where those minima or maximum points are. Okay, so Pierre Fermat explained how to do this. The key, he thought, was to look at tangents. And the points where we have maxima or minima relatively, locally, are the points where the tangents are exactly horizontal. Horizontal tangent corresponding to a maximum. Horizontal tangent here corresponding to a minimum. Okay, so in this case here we can study things because this is a parameterizable curve. If we think of x as being a parameter, then y can be expressed directly in terms of x. So if we set x, say, equal to t, then a general point on this has the form 1t at squared plus bt plus c. This is the x coordinate, this is the y coordinate, this is projective coordinates. A second point on the curve, the same expression, but t replaced with another value u. So now we have 2 points, t and u with parameters, and we can find the join of those 2 points. That's the secant line formed by 2 points on the curve. So 1 point on the curve, another point on the curve, and now we're finding the line through them. Okay, so we have to take the product of these 2 points, and we know how to do that. The first component will be the second one here times the third one there, and then minus the third one times the second one. The second component will be obtained by taking the third component here times the first component here, minus the first component times the third component. So we just get at squared plus bt plus c minus au squared plus bu plus c. So the c's will cancel, and we'll just have at squared plus bt minus au squared minus bu. And finally, the third component is obtained by looking at the first 2 entries here, 1 times u minus t times 1, which is just u minus t. Now, happily, each of these 3 components has u minus t as a factor. In other words, if u happen to equal t, then each one of these 3 components would be 0. Of course, we're not allowing that to happen because we're assuming that the 2 points that we're taking a secant of are distinct. So if we factor out, we get t minus u, say, times c minus atu. So what happens when you simplify this and factor it? When you simplify this and factor it, you get t minus u times b plus at plus au. And here we just rewrite it as minus t minus u. So we're in a happy position now because we can then remove the common factors of t minus u because this is all in projective coordinates. Okay? And t minus u is a non-zero factor. It's common in all 3 terms, so we can eliminate that. Okay, so we had our 2 points A and B on our quadratic curve. A in affine coordinates given by that expression, B given by a corresponding expression with u. And now we've just calculated the equation of the line joining them. So after we cancel that common factor of t minus u in the previous expression, we get in projective coordinates c minus atu to b plus at plus u to minus 1. So that's the equation of the secant AB. And now, to get the tangent, what we do is we take this expression for the secant line and set t equals u. That's all there is to it. So we replace u with t. We get c minus at squared. Here we get b plus 2at minus 1. That then is the equation of the tangent at A, the point parameterized by t. Okay, so that's a line. So that's the line. If we wrote it out in coordinates, it would be c minus at squared plus b plus 2at times x minus y. When is this horizontal? Right? That's what Fermat tells us. He says we should look at this tangent and try to decide when it's actually horizontal. Well, it's going to be horizontal when there is no x component, when it's of the form y equals something. Okay, so it's this thing plus this thing times x minus y. So it'll be horizontal precisely when this coefficient of x is 0. In other words, when b plus 2at equals 0, or solving, t equals minus b over 2a. So exactly one parameter value corresponds to a tangent which actually is horizontal. So we found the t value for either a max or a min. Okay, in that case, what actually is the equation of this line? Well, if we plug back into here, we've set this equal to 0. This is still going to be minus 1. And over here now we get c minus a times this value squared. So we square this, we get b squared over 4a. We multiply by a, we get c minus b squared over 4a. That's the equation of the line. So in regular form, this would be y equals c minus b squared all over 4a. And so the actual vertex here, where the minimum takes place, say v, maybe we'll write it there, okay, where we have a max or min, has x coordinate minus b over 2a, because that's the value of t. And now the y value is this thing here, which we can simplify by bringing it over a common denominator, 4a. We get 4ac minus b squared over 4a. So we've solved a fundamental problem in sort of elementary calculation of tangents, finding where we have a max or a min on a general quadratic function. There's exactly where the minimum or maximum value is going to be occurring, and it's going to be either a minimum or a maximum depending on whether a is positive or negative. If a is positive, it's a minimum. If a is negative, it's a maximum. Now this particular maximization problem of finding the vertex of a parabola, the top or the bottom, depending on which way it's opening, is almost surely the most common and the most important type of maximization problem in mathematics. And because it's so important, it's useful to understand it in a variety of ways. And I want to also show you the classical way of obtaining essentially the same kind of information, which doesn't really require any kind of calculus thinking, and it's purely algebraic. And hopefully it's something that you've studied in school along the way of deriving the quadratic formula. So I want to recast or review the quadratic formula and the usual story behind that. I want you to think about it in a certain way. Okay, so this procedure actually remarkably, I used to think that it goes back to Al-Khwarizmi in Arab work, and they were certainly the sort of people in the modern times, relatively modern times, who discovered this. But in fact, the completing the square story really goes back to Old Babylonian times as well. So 2000 BC, the Babylonians knew about completing the square. It's very remarkable. They didn't have algebra like we do, but they had a concrete geometrical way of essentially understanding the same story. But we're going to present it algebraically because we like algebra. Okay, so here's the starting point. There's our quadratic expression, y equals ax squared plus bx plus c. And what we're going to do is we're just going to rewrite this, just using simple algebraic rewriting. Okay, first of all, we're going to take a common factor a for these two first terms, the terms involving x. So I'll rewrite this as a times x squared plus b over ax, and still plus c at the end. And then we're going to attempt to complete the square by adding a quantity there. So we're going to take half of the coefficient of x, so that's b over 2a, and we're going to square it, and we're going to add it inside the brackets. To compensate for that, we're going to have to subtract the same quantity outside the brackets. So we're going to subtract b squared over 4a, not 4a squared, because there's an a also multiplying here. Okay, so if we subtract b squared over 4a, that exactly compensates for the plus b over 2a squared that we've put inside the brackets there. So equality is still maintained. And then we recognize that this is a perfect square. This is x plus b over 2a all squared, because it's the square of the first term and the square of the last term, and here is twice the product. And this thing here we can put over a common denominator, much as we've just done previously, 4ac minus b squared over 4a. And so here's another way of seeing what the maximum or minimum of this function or this expression involving x has to be. So the minimum or the maximum occurs when x equals minus b over 2a. So you see that whatever this number here is, this quantity here is always either going to be positive or negative depending on the sign of a. If a is positive, then this will always be positive. And then the whole thing will always be bigger than or equal to this thing. And in fact, it'll be minimum when this is 0. That will be the minimum possible expression because this is always going to be positive. And so the minimum is going to occur when x equals minus b over 2a, and that minimum will be exactly this value here. On the other hand, when a is negative, then this quantity is always negative. And then this quantity is the biggest possible value this expression takes. And it'll still take that biggest value when x is equal to minus b over 2a, and that biggest value will still be this thing here. So in both cases, the maximum or the minimum occurs exactly when x equals minus b over 2a, and that actual value that's taken on is always 4ac minus b squared over 4a. It happens to be a minimum when a is positive and a maximum when a is negative. So this is the same conclusion that we've reached in the previous analysis by looking for actual tangents. We can see that it's really an algebraic thing. We can get at it purely algebraically, so exploiting the fact that squares are always positive. That's the crucial sort of algebraic aspect here. Okay, so I want to connect that rewriting of the quadratic expression to the quadratic formula that you all memorized since you were very young people. But I want to start you to think about that formula in a different way. Okay, we're not going to want to think about the formula in exactly the same way here in the algebraic calculus. So the starting point is ax squared plus bx plus c equals identically this expression here that we've just computed. And suppose that we're interested in setting this equal to 0 and solving for x. We're interested in, are there any solutions? Are there any values of x for which this expression equals 0? And if so, what are those values of x? Okay, so instead of working with this, we're going to work with this. Okay, and we're going to rewrite this equals 0 in the form x plus b over 2a squared equals, so we're going to bring this thing to the other side where it becomes negative, and we're going to divide by that coefficient a. Throughout, we're assuming a is non-zero. So we divide by a, there's then a squared in the bottom. And over here we get b squared minus 4ac over 4a squared. So solving this thing equals 0 is the same as solving this. This is a perfect square on the left-hand side. On the denominator here, we see that this is also a square. So in order for this to have a solution, we're going to want this whole thing to be a square. That's really the same as having the numerator be a square. So this has a solution precisely when this numerator, b squared minus 4ac, which we might call delta because it's a rather important quantity, when that quantity is actually a square. In other words, when it's equal to r squared for some number r. That's the condition for which we're going to be able to actually solve this. And if that is the case, so if b squared minus 4ac is equal to r squared, then we can solve things because then this thing here is going to be the square of r over 2a. It's going to be r over 2a squared. And so x plus b over 2a is going to be either plus or minus r over 2a. So we can capture both of those in this somewhat loose expression where we use this plus or minus sign. X equals minus b plus or minus r over 2a. Or if we want to be a little bit more expansive and list the possibilities exactly, we might say x1 equals minus b plus r over 2a is one of the solutions, and the other one is x2, which is minus b minus r over 2a. So the solution here, this form of the quadratic formula, does not crucially have a square root involved. We're not going to say the square root of b squared minus 4ac, or we'd rather avoid saying that because the square root is so laden with these complications and different interpretations. So we'd rather say it more precisely. We'd rather say that this thing has a solution precisely when this quantity is a square. And if it is a square, then in terms of writing it as r squared, we can write down the solutions as minus b plus r over 2a and minus b minus r over 2a. And in this case, Then furthermore, the original quadratic expression factors is a times x minus x1 and x minus x2, where x1 and x2 are exactly these values here. This is sort of how I would like young people to learn the quadratic formula. Okay, I'd like young people to learn the quadratic formula by first learning this crucial rewrite of the quadratic expression. And then secondly, understanding that in order to solve the thing being 0, this quantity here, this crucial quantity, sometimes called the discriminant, has to be a square. And if it is a square, if it's r squared, we actually introduce a letter or a symbol for the thing that's whose square is going to be what we're interested in. In terms of that, we can write down then the two solutions. So I want to emphasize to you that a general quadratic expression is not always factorizable. So contrary to the fundamental theorem of algebra kind of belief system that we have currently, it's actually a rather special situation when a quadratic expression like this factors. Okay, so if you take any two linear factors, x minus x1 and x minus x2, x1 and x2 are numbers, you expand it out and then you multiply by any number n, you will have a quadratic expression. And that quadratic expression is very special. It's special because you've cooked it up as being a product of two linear factors. And I want you to appreciate that that's not the typical story. If you just randomly choose an expression like this, chances are it's not going to be of this form. These are very special kinds. Okay, so, but if we do have such a special kind of situation, which is still very important, we have to be able to connect what we've just learned about it with the previous formula for the vertex. So here's the picture that we then have. This parabola, well, it could open either downwards or upwards depending on the sign of a. I'm now showing you a story where a is negative, okay? In this case, the two places where it crosses the x-axis are actual numbers. There's actual numbers here called x1 and x2, and the parabola actually goes through those points. Not just approximately, but exactly. And that's obvious because we've started out with this factorization. In that case, this vertex v, which we know in terms of the coefficients a, b, and c, is minus b over 2a and 4ac minus b squared over 4a, that can be rewritten in terms of x1 and x2. So the x1 and x2, the midpoint, turns out to be this x-coordinate. In other words, the vertex is indeed sort of halfway between the two zeros. And the y-coordinate, the y value of the vertex, is minus a x minus x2 squared over 4. So up to a multiple, it's the difference of the two zeros squared. But I want to express to you again, all right, this is the exception, not the rule. You have a parabola like this, there's no guarantee that it actually meets the x-axis, even though it may appear to cross the x-axis, it may appear to, but that doesn't mean that you're going to actually find two exact points that are lying on the x-axis and the parabola. That's a very special case. Okay, we could call that the case of the factorizable quadratic. This is algebraic calculus. We have to be honest about what actually happens. And even though we might want every quadratic that appears to factor, it's just not the case. You can test it out yourself. You just write down a random quadratic and try to factor it, and you'll see you're not going to be able to do it. All right, now let's go to the cubic case and look for maxima and minima for a cubic polynomial, where things are more complicated and sort of richer as well. So y equals ax cubed plus bx squared plus cx plus d, a general cubic polynomial. And roughly the graph looks typically something like this, at least if a is positive. Okay, as an algebraic curve, we could rewrite it in a more standard form. If we sort of start with the lower degree terms, there would be d plus cx minus y plus bx squared plus ax cubed equals 0. Okay, so let's apply our algebraic curve orientation to try to find the equation of a tangent at some point rs on the curve. So we'll assume that the point rs lies on the curve, and we're going to attempt to find an equation for the tangent to the curve at that point. So let me remind you what you do. That what we are going to do is in terms of shifting our orientation. So instead of having an x and a y like this, we're going to have an x-axis or a new x-axis up here and a new y-axis here. So we're going to shift the x-axis and we're going to shift the y-axis. And we're going to do that algebraically by just this simple replacement substitution of new variables. So the old variable x will be the new variable x prime plus r, and the old y will be y prime plus s. And then we can take the existing equation and rewrite it in terms of x primes and y primes. So we replace the x with x prime plus r, there, there, and there. And we replace the y with y prime plus s. And then we expand this all out. And the constant term is going to be 0. We don't actually have to do a lot of work for that because it's going to be obvious that the constant term is 0 because we're arranging things so that if we plug in x prime and y prime equals 0, it means we're basically evaluating at that point. And we know that that point lies on the curve, so by definition that's going to be 0. So the constant term is going to be 0. That's the assumption that the point rs actually lies on the curve. What about the linear terms? Well, if we sort out where the linear terms in x prime are, where they're going to be. There's going to be a c there. We're going to find a linear term here. There'll be 2 rb from there, a coefficient of x prime. And over here we'll also get a coefficient of x prime because when we expand this with the binomial theorem, there will be a 3ar squared x prime appearing. So a coefficient of 3ar squared. So that's all the linear terms in x prime we're going to get. There's only a single y prime occurring with a minus sign there. And then in terms of the x prime squared and x prime cubed components, there's going to be a bit of that. So x prime squared will occur where? There'll be one right here. We'll get just a b times x prime squared. And over here we'll also get something because when we expand this, one possibility is to get 3 times a times r times x prime squared. And finally the cubic term, just a x prime cubed. So that's the expansion, and so this equation becomes this thing equals 0. And if we're interested in the tangent at this point here, well now this point is now replaced with 0, 0. We're in the place of having a grounded cubic now. And so we can read off the tangent just by reading off what the linear terms are, just this part right here. Those are the linear terms in this new cubic. So if we rewrite it, we get y prime equals c plus 2br plus 3ar squared times x prime. And then to translate back, to go from that equation to the original coordinates, we have to replace the y primes and x primes back with things involving x and y's. So the y prime is replaced with y minus s, the x prime is replaced with x minus r, and then we get a new equation just involving y and x. And that turns out to be y equals c plus 2br plus 3ar squared x, essentially the same, plus a few extra terms, plus an s, minus the same quantity times r. That's then a linear equation in x and y. But it's not actually quite as reduced as it could be because this constant term here can be simplified a little bit. It can be simplified because we're assuming that rs actually lies on the curve. So there's a relation actually between r and s, right? If we know what r is, then s is going to be given by this expression here. So if we replace this s with the corresponding expression in r, then this is going to simplify a little bit. Let's see what we get. Okay, so we now have the equation for the tangent to this cubic curve, this general cubic function, at a point rs on the curve. it's given in projective coordinates by this expression. D minus BR squared minus 2AR cubed, and then C plus 2BR plus 3AR squared to minus 1. So picture cubic is something like this. If we're given an x coordinate, say R1 or R2, we get a point on the curve. We're actually looking for the points where the tangent is horizontal. So we're now having to examine this and say, when is this tangent line giving us a horizontal line? Well, just as in the quadratic case, we get a horizontal line when this coefficient of x in the equation is 0. So that it's something plus 0 minus y equals 0. That's y equals something. That's a horizontal line. So the condition is that c plus 2br plus 3ar squared is 0. Now that's a quadratic equation in R. Okay, so we expect that it may or may not have solutions. So quadratic equations don't always have solutions. But when they do have solutions, typically they have two solutions, although occasionally they can have one. And which of these cases do we have? The quick way of deciding that is to look at the discriminant of the quadratic equation. Okay, so what is the discriminant? So we take the coefficient of r, which is 2b, and we square that. And we subtract 4 times the product of the coefficient of r squared and the constant term. So 2b squared minus 4 times 3a times c. Well, there's a common factor of 4 there. When you pull that out, then we also get b squared minus 3ac as the other factor. And now the general theory of quadratic equations tells us that we are going to have solutions precisely when this thing is a square. Now 4 is always a square. So it all comes down to whether b squared minus 3ac is a square. That's the condition on having places where the tangent line is horizontal. Now, of course, this is quite a familiar looking kind of thing, almost, because it looks like the discriminant of a quadratic equation, which you remember as b squared minus 4ac in some slightly different context. So it's interesting that there's a little bit of a variant here. It's this particular quantity that you calculate from the coefficients of the cubic, and d is not relevant. It's this particular expression that tells you whether you're going to be able to find places where you actually have horizontal tangents. And these vertices, which we might call them, are also sometimes known as stationary points. But where exactly are these things? What is the actual position of these vertices if we can find them? So there's a little bit of algebraic playing around here that we can do. So this is the condition to have horizontal tangents. And if this condition is satisfied, so we have some value of r that satisfies this, then this y-coordinate, d minus br squared minus 2ar squared, can be rewritten because this quadratic here really allows us to replace r squared with linear and constant term things. So we could make substitutions to simplify this. And I'll leave it to you as an exercise. It'll be talked about in the work problems of the course, that you can then simplify this to get this more complicated looking, but ultimately simpler expression in just the single linear variable r and a constant. So it's minus 2 b squared minus 3ac, that same quantity, times r, plus 9ad minus bc, all over 9a. That then is going to be the y-coordinate associated to the r values where the maximum and the minimum are occurring. So in other words, if we have a picture like this, and say one of the max is going to be at r1 and the other max is going to be at r2, so we're assuming that b squared minus 3ac is a square, then these y values here are going to be given by this expression here. So for example, if you're a high school teacher and you want to cook up examples where your students can actually compute the maxima and minimum, then you're going to have to choose your cubic a little bit carefully. In fact, you're going to exactly want to choose the coefficients so that the b squared minus 3ac is a square. If you do that, then you're good. Then you're going to be able to find exact places where those vertices are happening. Now, this is quite a rich story, and I want to finish by pointing out I think really sort of the heart of the matter is not actually necessarily these values here, but actually the center of this cubic. So it turns out that such a cubic polynomial actually has a center. It has a point of symmetry, which is actually lying on it, pictured right there. And it turns out to be exactly the midpoint between these 2 points here that we've just found. It's the midpoint between the 2 vertices. And in the word problems, I'll lead you through finding this thing and verifying that it actually is a center in the following sense. That if you have any point on the cubic and you look at that vector there and go an equal vector in that direction, you'll find another point on the cubic. So there's an affine symmetry. It's an affine symmetry about that point there. So I made this calculation and I looked on the internet to see if, obviously this is not going to be the first time this has been made. Well, it turns out that Michael de Villiers, who's a prominent geometer and educator from South Africa, has written a little paper in which he writes down this formula. So perhaps it's a formula due to him. So I will give it credit to him. This is the formula that we get. The point is minus b over 3a, and this y-coordinate is d plus b times 2b squared minus 9ac all over 27a squared. That's the formula for the center of the cubic. So illustrating that there's actually quite a lot of geometry hidden in these functions, and we must not be too scared about relatively more complicated things. So we're going beyond the quadratic case. It's not just 4ac minus b squared over 4a squared and stuff like this. There's a little bit more complicated stuff. All of the coefficients are being involved, and there's actually quite a lot of other secondary questions that we can investigate and things to discover. And of course, suggesting that what happens when we go to higher degree curves, well, there's just an enormity of interesting things that are waiting to be discovered, and that already have been discovered because people have been thinking about these things for hundreds of years. So there's much to learn. I'm Norman Wildberger. Thanks for listening.